exercise was more to see a solution, complete solution of the governing equations more than anything else, which we did here. But as I'm emphasizing, you need to address also the bending moment and the interlaminar stress issue to complete that design problem. Another case that we will try to solve exactly involves a plate with a point force, transverse or vertical point force, which can be anywhere acting on this plate. We assume again a symmetric layup, so the B matrix is 0. We assume that D16 and D26 is 0. And why do we bother? Is because, first of all, walking loads, step loads, especially if you have high heels, which is concentrated, quite concentrating the load, are essentially a floor with a point load. More importantly, impact. Impact is, of course, a dynamic problem. We'll talk about that in the next quarter much more. But as a first cut, especially for a series of impact problems called low-speed impact situations, you can start the solution by trying to solve this problem of a point force acting on a anisotropic plate. And we are assuming simply supported conditions. And we need to get our governing equation. Now, we saw the governing equation before. Where am I? If you look at the bottom here, this part is what is derived here, and this part is what we will be using in here. But to see more exactly what's going on, from the equilibrium equations shown here in terms of shear forces and bending moments, we have this equation. QZ is, minus QZ is the out-of-plane load. If I take my QX and QY definitions, or from the equilibrium equations, which are in terms of the moments, I can substitute in this to arrive to this equation here. Now, in the slides posted, this says 0. It's obviously a mistake. It should say minus QZ. It's the right-hand side of this equation here. Now, each of the moments can now be replaced through our ABD matrix relationship. And because we said the B matrix is 0, then it's just directly involving the D11, D12, D16 terms, and so on. And because I said D16 and D26 is 0, I can replace these moments with these products, D11 times kappa x plus D12 times kappa x, kappa y, and so on. When we do this, we arrive at exactly the same left-hand side that I just showed you from before. And the right-hand side is still my out-of-plane load. Now, our out-of-plane load in this case is a point force. And I can write that as a distributed load, the word distributed in quotes, by using Dirac delta functions. If I take my magnitude, the force F, delta x minus x0 means that this quantity is 0 everywhere except when x equals x0, in which case it's equal to 1. And similarly, delta y minus y0 is 0 everywhere except y equals y0, in which case it's equal to 1. So that's a convenient way of writing a load, a point load, in terms of a distributed type of function, which becomes very useful in the next slide. We said it's a simply supported plate, so we will assume now for a solution to this governing equation, a solution that satisfies simply supported boundary conditions. W is the out-of-plane deflection, and at x equals 0 or a, and y equals 0 or b, because of the signs being present, W is 0. So that satisfies the boundary condition. And this one, compared to the previous one, which was a single Fourier cosine series in y, now it's a double Fourier series because I have both the x terms and the y terms in terms of signs in this case. That allows me to go back to my governing equation at the bottom left here, and substitute for W all these derivatives of W. But you can obviously see that these then would give me double summations of sign terms. And on the right-hand side here, I have this peculiarly looking expression, which is just a point force at one location. So the only way to proceed, if I want to insist on this Fourier series business, is to actually replace this with its corresponding Fourier expansion. Remember, the advantage of the Fourier series is that if you have any function that's reasonably well behaved in terms of its continuous or its piecewise continuous, and its first derivative somehow can be defined everywhere and so on, then that function can be represented by a Fourier series. So we will do the same thing here and replace this by a Fourier series. The Fourier series will have this form, and the BMN are unknown coefficients. And we use on purpose the signs here because we have signs in the W expression, so that when we substitute in the governing equation, we'll be able to match terms of the same coefficient, coefficients of the same term, sine times sine. To determine the BMN, we go back to Fourier series theory, which says take your infinite series, which is shown here, multiply each term by the orthogonal function. So wherever I have a sine m pi x over a, I'll multiply by sine, where is it? Sine p pi x over a, where p now is an integer. And similarly for the y dependence, I will have my original sine n pi y over b, but I also add my sine q pi y over b. I multiply that, and I integrate over the entire plate. If I did it on the right-hand side, I have to do it on the left-hand side also. Remember, all I'm doing is I'm operating on this expression here. I take this expression, in order to find BMN, multiply both sides by sine times sine of different integers, p and q, and integrate over the entire plate. Now, from Dirac delta functions in your basic physics, I hope you remember that the integral of a function that involves the Dirac delta function means you evaluate the function at that location. So basically at x equals x0 and y equals y0, I will just, this double integral becomes f because that's my constant, and then these signs will be evaluated exactly at that same location. Now notice I have p and q there, and now this became m and n. It became m and n because my right-hand side will only have a non-zero contribution when m equals p and n equals q. So there's no need to stick with p and q because the right-hand side would be 0. And I will only, and I'm trying to calculate BMN. So I can replace directly the p and q on the left-hand side with what I know from the integration on the right-hand side will be my only non-zero terms. To make a long story short, my BMN times AB over 4 has to equal this left-hand side, so I can calculate my BMN. And knowing my BMN, I can go back to my series expression here, substitute W in my governing equation on the left-hand side, substitute the BMN sine times sine on the right-hand side, and equate now the coefficients of the different terms of, that have sine m pi x over a and sine n pi y over b. When I do that, I will find now that my a and n terms, which is what I was looking for in the first place for the W expression, are given by this mess, as a result of which my W now, just by taking this and putting it in, is given as is given at the bottom of this page, and that's valid for any xy location and for any x0, y0 location where the point force is acting. Of course, the special case is the force acting in the middle, which gives us the largest deflection. In that case, by substituting x0 is a over 2 and y0 is b over 2, you can show that this is the center deflection. Remember, that's for a simply supported plate for which d16 and d26 is 0, and the layup is symmetric, so the B matrix is 0. So, okay, big deal. You got W. You were talking earlier about impact. So what do you do with this? Somehow, I have to relate my impact energy, this dropped object, to a certain force. Once I know that force, the maximum force during impact, I can do the solution I just did. That gives me the displacements. And that's not even half the story. I have to translate these displacements into usable strains through the structure, which is mostly what you are doing in your homework 1 right now. So I make the W's into strains, and once I have strains, I can then either use them in a strain-based criterion or translate them further into stresses if I want through stress-strain equations, and use a stress-based criterion, and that will give me an indication of which ply fails And again, the next step would be, okay, I failed at some location, what happens next? And that's where we'll talk about in the second quarter, the next quarter when we talk about impact. But this kind of starts giving you the logic, and it can be quite useful as a starting point for the real impact problem